Okay, so it's talking about these humerus bones, or the molluscus primate, whatever they're called, and it has a mean ratio of mu equals 8.9. So I'm going to go ahead and create my split screen here, and go ahead and write here mu equals 8.9, and I think it's in centimeters. Oh, it's a ratio. Okay, so we'll just leave it as 8.9. Mean ratio. And so we've got all that information, and they tell us that alpha is 0.05. And so we put all these numbers into a list. We put them all in to L1 or L2 or whatever, and there's 41 numbers. Okay, so N equals 41 bones, humerus bones. It's not very funny though. And we're assuming that they're a random sample, it says. Okay, so I'll go stat, calculate 1 var, L1, and I want to find my X bar is 9.26. My standard deviation of a sample is SX. Let me make a little bit better X there. Equals 1.198. I'm going to go one more place value beyond what my mean is. Okay, we know that degrees of freedom is going to be 40 because N was 41. It's always one less than that. What else do I need here? 1, 2, and I'm doing a hypothesis test. Yep, test with the population. So here's my null hypothesis is this, mu equals 0.89, or 8.9, sorry. And my alternative hypothesis is going to be, those are colons right there, by the way, folks, is that mu, it differs from that, so it's going to be not equals to 8.9. Okay, are you so far so good with that, Cherokee? Okay, so we got to have these 8 things each time. Then we slide over, because now we have to talk about the conditions. We're assuming it's a random sample of bones. Random sample. Of humerus bones. And 41 is less than 10% of all the bones around the site. And then the third thing is our histogram. So to create the histogram, we've got to go second y equals. I got to turn this plot on. And then we have to select the histogram, which it has here. And we're using L1 because that's where we put our numbers. And then we zoom 9. Okay, as I look at that picture, I can say, well, that looks okay, but what if I change my window and see it goes from 6 to 12.9. So I'm going to go from 6 to 13, and I'm going to go by ones. Let's see what that looks like. Okay, there's a little bit of a gap there, so I'm going to do this, stat, whoops, I'm sorry, go back to window. I'm going to make my scale 2, make this 14. I'm going to graph that. Whoops, that's a little bit too much maybe. Just be patient with me here just for a moment. All right, I like the 1 better. Make that 1, graph. And so I'm going to draw this rough sketch of this histogram. And it's okay, there's a gap there. That's not that big of a deal. Whoops, that's supposed to touch right there. That didn't quite make it. And we're going to say that, yeah, it's roughly symmetric. Roughly symmetric. Sorry, my spelling's bad today. And it is unimodal. That's obvious. Okay, so since those three conditions are met, we're going to do a one sample t-test. Okay, and to do the t-test, we go stat, over to test, and it's the second one. But before we do the t-test, we have to show this. We have to show our standard error. Whoops, sorry. Our standard deviation for this problem is going to be 1.198 divided by the square root of n, which is 41. Now, I'm not even going to write that number down. I'm just going to write that. Then I'm going to say that my t-value has to equal x bar, which we found, minus mu, which we were given, divided by our new standard deviation. And that's going to equal, see, I'm not going to punch either one of these two into the calculator. I'm just going to give the numbers or the formula, and then I'm going to run the t-test. I'm going to go using data. Mu is 8.9. Using L1, it's not equal to. Whatever's here, the alternative is what goes on this row. And we said it was not equal to. Whatever's here goes up here at the top, at the 8.9. Okay, so we're going to calculate, and there's our number. We get a t-score of 1.928. 1.928. And we get a p-value. Here's my probability that t is going to be, we're going to say greater than 1.928, because we're going to do it both sides. We're going to multiply that times 2 because it's two-tailed with the not equal to here, equals 0.061. Okay, now here's my p-value, my probability value. Well, compared to alpha of 0.05, this is bigger. Okay, this number is bigger than this number, so with a p-value larger than alpha, we fail to reject the null hypothesis. We failed. This is the null hypothesis. There is not enough evidence to suggest the population mean for this species, which I'm simply quoting this up here. Test whether the population mean for the species that left these bones differs from 8.9. There's not enough evidence to suggest the mean for the species is different from 8.9. Whoops. Okay, so that's that side. Okay, so now let's do the confidence interval on the other side. On this side, it said a factory soft drink machine dispenses 12 ounces into cans. This is just like the coffee question that we've already done. Simple random sample of 35 cans, so N equals 35. That means my degree of freedom equals 34. Also, it tells us that the mean is 12 ounces, so mu equals 12 ounces. But then it says the mean content of the 35 cans that they've measured is 11.2. So my X bar is 11.92 ounces. And my standard deviation is 0.085 ounces. And they want us to create a confidence interval. Okay, so it's a random sample. $35 is less than 10% of all those. All cola cans, or cans of cola. And now here's a new thing that we're going to throw out there. 35 is greater than 30, so it is large enough for a normal sample. Any number greater than 30 is great enough for a normal sample. Okay, so we can do our confidence interval. So CI equals X bar plus or minus T star times my standard error.